Welcome to this explainer. All right, today we are going to become chemical detectives. Our mission? To decode and completely solve two very specific equation puzzles derived directly from our source text. If you've ever stared at a chemical reaction and just wondered how scientists make the math work out so perfectly, you're in exactly the right place. We're going to break the whole thing down step by step. So, right out of the gate, our source material challenges us with two written reactions. Just words, like hydrogen plus chlorine. But our goal today isn't just reading. It's translating these words into precise, mathematically sound chemical formulas. We aren't just writing letters on a screen here. We're literally balancing the scales of nature. But hey, before we start, it is absolutely vital to understand what we actually mean when we say a balanced equation. Honestly, just think of it like an accounting ledger. It's a representation where the exact number of atoms for every single element is completely identical on both the starting side, what we call the reactants, and the ending side, the products. Every single atom has to be perfectly tracked and accounted for. There are no disappearing acts in chemistry. Okay, here's our roadmap for this explainer. We'll establish our balancing methods, solve a simple introductory puzzle, tackle a crazy boss-level equation, and finally, review our balanced results. Let's dive right into part one. The balancing act begins. It's time to establish our detective method. So, we are going to strictly follow these three steps for every single problem we encounter. Step one, translating the words into chemical symbols. Step two, tallying the atoms on both sides to see exactly where the imbalances are. And step three, strategically adding coefficients, those big numbers in front of the molecules, to balance the scales out. If we stick to this process, we can solve literally any equation our source throws at us. Moving on to part two, puzzle one, simple synthesis. Let's warm up with a simpler reaction. All right, here's our first prompt from the text. It's a classic synthesis reaction. We start with hydrogen and chlorine, and they combine to form hydrogen chloride. Now, it sounds super simple when you read it out loud, but we need to see what this actually looks like structurally. Applying step one of our method, let's translate those words into symbols. On the starting side, we've got the diatomic molecules H2 and Cl2. Notice those little subscript 2s? That's just how these elements naturally exist in the wild. And on the other side, they yield HCl. But, as you can probably already see just by looking at the letters and numbers, something isn't quite right. Looking at our initial atom count ledger, it clearly exposes this mathematical imbalance between our starting materials and our product. See, our reactants have 2 hydrogens and 2 chlorines, but our product side, it only has 1 of each. We're missing atoms, and that completely breaks the fundamental rules of chemistry. So, the crucial turning point is realizing we just need to drop a giant 2 right in front of the hydrogen chloride to fix this entire puzzle. Remember, we can't ever change those little subscript numbers, but we can change how many of the whole molecule we have. And our updated ledger is now perfectly balanced. By adding that coefficient of 2, multiplying both the H and the Cl on the product side, we prove that we now have exactly 2 hydrogen and 2 chlorine atoms on both sides of the arrow. The ledger is perfectly even. With the math completely checking out, we can triumphantly close the case on our first puzzle. The final perfectly balanced chemical equation is H2 plus Cl2 yields 2HCl. Great job. But now that we've got the fundamentals down, it is time to ramp things up. Which brings us to part 3, puzzle 2, the boss level. Let's tackle the complex equation. Oh man, look at this one. The source text raises the stakes considerably here. We're combining barium chloride and aluminum sulphate into what's known as a double replacement reaction, yielding barium sulphate and aluminum chloride. Honestly, it's a mouthful just to say, and it looks like a total nightmare when we go to write it out. Translating this into symbols reveals this tangled web of polyatomic ions and subscripts. We've got BaCl2 plus Al2SO4 3. The arrow points to our products, BaSO4 plus AlCl3. Just look at all those numbers. It looks so messy right now, but remember our process. Deep breath. Step 2 is to tally. Counting the atoms on this ledger shows a seriously chaotic imbalance. The barium looks okay at first glance, 1 to 1, but look at the rest. Chlorine is 2 on the left, 3 on the right. Aluminum is 2 on the left, 1 on the right. And that entire sulfate group, the SO4, we've got 3 on the left and only 1 on the right. The whole thing is completely out of whack. To start unraveling this knot, our best detective move is actually to place a coefficient of 3 right in front of the barium chloride. Why? Because we need to target that uneven chlorine count. The left has 2, the right has 3. The lowest common multiple there is 6. So putting a 3 in front of BaCl2 gets us up to 6 chlorines on the left side. Now, visualizing the aluminum sulfate reveals this really tricky 2 to 3 proportion of aluminum to sulfate that we're dealing with. We have to simultaneously try to accommodate this ratio on the right side of the equation. We've got 2 aluminums and 3 sulfates that desperately need homes on the product side. Okay, it's like a domino effect. Since we put a 3 in front of the barium on the left, we obviously need 3 bariums on the right, so we add a 3 to our barium sulfate. This conveniently and beautifully also gives us the 3 sulfates we needed. Then we add a 2 to our aluminum chloride. This gives us the 2 aluminums we needed, and magically, well, mathematically, 2 times 3 gives us exactly the 6 chlorines we generated on the left side. We just forced the remaining stubborn atoms into perfect alignment. Check out this beautifully satisfied ledger. Just look at those numbers. Barium is 3 to 3, chlorine is 6 to 6, aluminum is 2 to 2, and the sulfate groups are 3 to 3. They are completely equalized across the board. Nothing was lost, and absolutely nothing was magically created. We have officially conquered the boss level. By systematically tracking our atoms and tweaking those coefficients, we ended up with this mathematically sound, perfectly balanced equation. Seriously, take a second to just appreciate the pure logic of it. All right, bringing it home with part 4, the final balanced results. Let's quickly review our hard work. We successfully transformed 2 brief, text-based word prompts from our source into these 2 visually balanced, chemically perfectly accurate formulas. We took the language of words and translated it into the universal language of atoms and mathematics. Pretty cool, right? So, as we wrap up this explainer, I really want to leave you with this thought. Ask yourself, if this rigorous accounting of microscopic atoms proves that absolutely nothing in our universe can ever be created or destroyed from nothing, how does this unbreakable rule of conservation apply to the everyday physical world around you? Every single breath you take, every fire that burns, it's all just a grand, beautifully balanced equation. Thanks so much for joining me on this chemical detective journey today, and keep exploring.